So now that we've been going through functional programming and sequential streams for the first 7 weeks or so, it's time to finally transition into the parallel processing part of the course, which, as I mentioned before, leverages everything we've talked about, so it wasn't a waste of time. And we're going to talk now about the Java parallelism frameworks. And as you'll see, there's a bunch of them. Some of them have been around for a while. Others have been added, quote, more recently, where more recently is 2014 and beyond. And they've continued to be enhanced and evolved over the last 5 years or so. The three main mechanisms we're going to talk about, and we're going to cover them in slightly different order than I'm going to present them here for obvious reasons if you take a look at your assignment. Number one, fork join pools. Number two, parallel streams. Number three, completable futures. And they all support different variants of parallel programming. Completable futures also provides a reactive asynchronous programming model. I should also probably point out that fork join pools are an object-oriented framework, not a functional framework. Parallel streams are a synchronous functional framework, and completable futures is basically an asynchronous functional programming framework. So each of these approaches has something a little different and a little special that it adds, and they relate to each other in cool ways. So the fork join framework was introduced back in Java 7, which came out in the 2010 time frame. And there's an excellent interview with the person who developed the fork join framework, my buddy Doug Lee, who's an expert in object-oriented programming, functional programming, C++, Java, patterns, concurrency, parallel programming. Amazing guy, done a lot of cool stuff, wrote most of the code that's part of the Java util concurrent package, and has had a very deep influence on Java in general over the past 25 years. Fork join pool is an object-oriented framework that gives you a high-performance, fine-grained task execution model for so-called data parallelism. And that basically means that we take the data and we split it up into chunks by forking. So you take some source of data and you fork, 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 fork until you have little atomic-sized chunks, kind of like your array split iterator. And then you take each of those atomic chunks and you run them sequentially in parallel. So you take a bunch of sequential computations and run them in parallel. And then you join them all back together again. So it's a classic MapReduce style problem, although a better term is probably split, apply, combine. That's kind of the way to think about this. The fork join pool framework is essentially about solving complex problems by splitting them up into simpler problems using divide and conquer as the programming paradigm. And I'm very proud of my animated GIF here that shows divide and conquer, right? So we take a big problem, we chop it up into smaller pieces, and then, of course, we would keep recursively chopping up those smaller pieces till we have a bunch of atomic-sized pieces. So here's kind of how it works. If the problem is small, then directly solve it sequentially. Otherwise, split the problem up into independent parts, fork new subtasks to solve each part in parallel, join everything back together again, and then get a single result from all the subresults. And this, of course, occurs recursively, so you end up with a tree of parallel processing, which basically, if you think about it, looks like this. So you have a tree of stuff that's been chopped up into little parts. Under the hood, there's some really, really cool features called work stealing that are used to maximize multi-core processor performance. So we're trying to keep the processor cores as busy as possible by making sure that if one core, one thread, doesn't have anything to do, rather than just sitting idle or putting itself to sleep, either spinning idly or putting itself to sleep, it will go and steal some work from some other thread or core that has work to do. And that way we can keep more things going on, even if each task takes different times to run. Yes, sir?
Will the equivalent of this be like in C using like p-threads?
Oh, great question. So the question here is, how does this correspond to p-threads? So if you're programming in C, like if you take the operating system course here, hopefully you'll learn about p-threads. P-threads stands for portable threads or POSIX threads, and it's a standard API for spawning threads in C. The equivalent sort of feature in Java would be Java thread. And so the fork join pool that we're talking about here, and we will go into much, much more detail about this shortly after we cover parallel streams, is that you have a pool of so-called worker threads that are Java threads. So if you were programming in C++, you could have a pool of P threads. So P threads, let's see. So there's really no equivalent in C to the concept of a fork join pool out of the box. So P threads are like Java threads, but in C as opposed to Java. And the fork join pool is a higher level abstraction that uses a small pool of Java worker threads to let a large number of so-called fork join tasks run in parallel. And so you see that as we talk about that in more detail, P threads or any kind of threads are the lower level mechanisms that make up the pool, but there's a higher level programming framework that manages how this all works under the hood. And it's really, really cool. OK, so that's basically the fork join pool. We'll talk obviously a lot more about that. Java 8 then came along and added some new frameworks that do parallel processing with a functional veneer, a functional facade. And those frameworks are first parallel streams, which takes the concept of a stream, which we've been talking about so far, and it allows the data to be broken up into chunks. So it partitions a stream into substreams or chunks, and then it runs those chunks in parallel on multiple cores in a pool of threads that are Java threads, and then it combines everything into a so-called reduced result. So if you think about this briefly, you split the data up into chunks using a parallel split iterator with a try-split method. Each of the chunks then runs in its own thread, and then when we get done, the terminal operation combines them all together again, and you get a single reduced result. So that's what parallel streams do in a nutshell. So it's streams where the stream is broken up into substreams. And these substreams are mapped to the threads and cores, so it all works very efficiently. And it leverages something called the common fork join pool. So I didn't really mention that over here, but with the fork join pool in Java 8 and beyond, they have a singleton common fork join pool. So it's a common set of threads, typically close to the number of cores on the machine, and a parallel stream or a set of parallel streams. All the parallel streams in a process will leverage the so-called common fork join pool. There are not a lot of other ways to process streams. They typically use the common fork join pool, and we'll talk more about that later when we talk about the common fork join pool and how it is used in parallel streams. So what parallel streams give you is this wonderful, fine-grained data parallelism functional programming model. So it gets the fine-grained data parallelism from the fork join pool, and it then kind of throws this functional programming wrapper or facade around the object-oriented fork join pool, so you now can program at a higher level using the streams model, which is functional, and then it maps those chunks into things it gives to the fork join pool to run in parallel. So that's basically parallel streams, and that's essentially a synchronous form of parallel processing. There's also an asynchronous variant of parallel processing called completable futures. And for reasons that may even be obvious just by looking at the pictures here, right? You kind of see streams. If you know what a sequential stream is, then going to parallel streams is pretty easy because it just runs the chunks in parallel, right? It's not a conceptually different programming model. They're both synchronous at their core. When we move into completable futures, you will see very quickly as we get into this that they are much more complicated. And that's because you end up with a bunch of asynchronous tasks that can run in parallel, and then they take the results as the asynchronous results complete. You can then chain together various so-called completion stage methods to handle the results. So we'll talk obviously a lot more about this, and I'll explain what this diagram means. But when you first look at this diagram, it's like, what the heck is going on? And what this is showing is how we can take our tasks and then split them up into a way where they can run in parallel. And as tasks finish, then they're so-called dependent actions or completion stage methods that can be called back automatically by the framework to handle the subsequent processing of asynchronous results as they complete. So this particular example is actually very similar to your image crawler where we get some start page asynchronously, and then once we've got the start page URL, or sorry, we've got the start page from a URL, then one task in parallel goes off and counts the number of images on that page, and then the other task in parallel goes off and recursively crawls all the links on that page that are reachable from that page and counts the number of images on those links that are reachable. So again, it's very similar to your program. And then when both of these tasks complete, we then take the results and we combine them all together to get a final sum. And we'll talk a lot more about this. These are basically asynchronous tasks that have dependencies on their completion, and as a result work very nicely in the completable futures framework style of programming. Now, all these different asynchronous tasks that are running can also execute in parallel in thread pools. And as it turns out, with the model that they have with completable futures, you can either use the common fork join pool like Parallel Streams does, or you can make your own custom thread pool. So it's also possible to make a custom thread pool and have that perform the computations. And that's different from Parallel Streams. Parallel Streams really tries to get you to use the common fork join pool, for better or for worse. So one of the other cool things that you'll learn, and you'll see this when we do the fourth and final project in the course, is you can actually combine completable futures and sequential streams together for good effect. You can have very nice program that uses streams to pipeline together computations that run asynchronously. And this is really, really, really cool. And you'll get a chance to play around with that in the fourth assignment. It's also possible to do completable futures without using streams too. That's also quite reasonable, but I like it when they get combined together. It's like a Reese's peanut butter cup, right? You take chocolate, you take peanut butter, you put them together, they're really tasty. For all the frameworks we're talking about, at least the, well, actually, all the frameworks, fork join pool, completable futures, parallel streams, one of the great things about them is if you do things right, you very rarely have to put any synchronization in your code at all, and you don't have to explicitly spawn threads. So threads pretty much disappear, synchronization pretty much disappears, and as a consequence, many of the accidental and inherent complexities of parallel programming disappear. So there's a lot less to go wrong with your code because you don't have to put locks in your code often. You don't have to spawn threads, pretty much never have to spawn threads. And so that makes everything a lot simpler. There are still a few cases where you have to lock things, but usually you would end up using some kind of data structure like a concurrent hash map or whatever. Another thing to note here is that the parallel streams and completable futures frameworks typically use the fork join pool under the hood to do their job. So all the effort that went into optimizing the fork join pool with work stealing and all these other cool mechanisms get leveraged by parallel streams and completable futures. Now, what we're going to do in this class is we're actually going to do parallel streams first. And I'll be talking about parallel streams starting next week. And the reason for that is that it's so obvious to take your sequential streams implementation for assignment 2A, and for assignment 2B, just change stream to parallel stream, right? It's just like falling off a log. It's real simple to do. Assignment 2C, which will come out shortly, will then go and make a more interesting parallel streams model. But it's still very simple. So we're just going to do parallel streams first. Then we're going to do the fork join pool. In a perfect world, it would actually be somewhat better to do the fork join pool first, because then you would see that all this complexity of the fork join pool just disappears when you use parallel streams. But it just doesn't quite work that way with the assignments. So after we finish 2C, which is the parallel stream version that's a bit more interesting, then we're going to redo the image crawler with the fork join pool. And you'll see that it's very powerful, but you have to do a little bit extra work yourself because you have to write the fork join tasks and so on and coordinate the steps a bit more explicitly, whereas parallel streams hide you from that detail. And then after we do that, then we will go and cover completable futures. So that'll pretty much take us through the rest of the semester, and you'll get a lot more knowledge about all these things. So as you probably already saw, parallel streams is pretty easy for the most part. Fork join pool takes more work, but it also can give you more power if your world doesn't quite work in a simple divide and conquer-like model that parallel streams provides. And completable futures is the most complicated, but also the most powerful approach. So we will talk about those starting next week.